NASA lost Artemis II for 41 minutes. Not because a system failed, not because the crew made an error, not because the deep space network went offline. The moon got in the way. That sounds almost embarrassingly simple. A rock blocked the signal. But the physics behind that rock and the engineering decisions that followed are anything but simple. This is no science, and today we follow Orion into the dark. Here is what most people assume when they hear communications blackout in space. They picture a signal getting weaker, stretched thin across hundreds of thousands of kilometers, eventually too faint to read. It's a reasonable picture. Distance weakens things. That's just physics. And if that were the problem, the solution would be obvious. Bigger antennas, more transmitter power, better receivers. NASA has all of those. The Deep Space Network operates dishes at multiple sizes: 70 meters, 34 meters, 26 meters, with the 70-meter antennas being the largest and most sensitive in the network. They've maintained contact with Voyager 1 more than 23 billion kilometers away, using signals so faint they carry less than a femtowatt of power. To put that in perspective, a femtowatt is 1/quadrillionth of a watt. These are among the faintest signals ever deliberately received by human-built hardware. So if the DSN can hear a spacecraft at the edge of the solar system, why couldn't it hear Orion at 380,000 kilometers? That question contains the misconception, and it's a seductive one. The assumption is that this is a power problem, a sensitivity problem, a technology problem that NASA simply hasn't solved yet. It isn't. The blackout during Artemis II's lunar flyby wasn't caused by distance at all. It was caused by geometry. And geometry doesn't care how powerful your transmitter is. To understand what actually happened, hold one number in your head: 3,474 kilometers. That is the moon's diameter. During Artemis II's lunar flyby, a crewed pass around the moon, not a landing, Orion crossed behind that entire mass of rock. No straight line back to Earth. No path for a signal to follow. Radio waves travel at the speed of light, approximately 299,000 kilometers per second. They cross the Earth-Moon distance in about 1.3 seconds. That 1.3-second delay is real, and it matters for mission operations. But it is not what caused the blackout. Latency and blockage are two completely different problems, and conflating them leads to completely wrong conclusions about what could fix this. Latency means the signal arrives late. Blockage means the signal never arrives at all. When Orion crossed behind the moon's limb, the curved edge of the lunar body as seen from Earth, it entered a region where no straight line exists between the spacecraft and any point on Earth. Radio waves at the frequencies NASA uses for spacecraft communications, S-band and Ka-band, cannot meaningfully penetrate 3,000 kilometers of basalt and anorthosite. The moon's composition and these frequencies combine to make the lunar interior effectively opaque to radio signals. Every frequency in NASA's spacecraft communications architecture stops at the lunar surface for all practical purposes. Engineers call this a radio shadow cone. The moon casts it the same way a lamppost casts a shadow, except the lamppost is 3,000 kilometers thick and the light is traveling at the speed of light. For approximately 40 to 41 minutes, Orion sat inside that cone. That duration isn't arbitrary. It's a direct consequence of Orion's flyby speed and the angular width of the shadow cone along the spacecraft's specific trajectory. During those 41 minutes, Mission Control at Johnson Space Center could not confirm Orion's trajectory, could not verify crew status, could not send a single command. If a thruster had misfired, if a pressure anomaly had developed, the crew would have been on their own, with no way to reach the ground and no way for the ground to reach them. That is not a technology gap. That is geometry doing exactly what geometry does. Place yourself inside NASA's deep space network for a moment. 3 facilities, 3 continents, designed so that as Earth rotates, at least one station always has an unobstructed view of deep space. Goldstone in California's Mojave Desert, Madrid in Spain, Canberra in Australia. Between them, they covered the entire sky, day or night, any season. This is one of the great engineering achievements of the space age, and during Artemis II's lunar far side pass, it was completely irrelevant. Here is the thing people get wrong about the Deep Space Network. Its power is continuous availability, the ability to always have a station facing the right direction. What it cannot do is transmit through a planetary body. That distinction is everything. When Orion was behind the moon, it didn't matter whether Goldstone was active, or Madrid was active, or Canberra was active. All 3 were active. All 3 were pointing correctly. All 3 were operating at full capacity. The moon was in the way. That's the whole explanation. No reorientation of an antenna changes that. No increase in transmitter power changes that. You cannot shout through 3,000 kilometers of basalt. We expect engineering solutions. We expect that if something doesn't work, you build a better version of it. The DSN is already the best version of itself. It still couldn't help. Because the moon's diameter is not a specification that NASA can upgrade. The geometry is fixed. The shadow cone is fixed. The only variable is where you put your relay infrastructure. And for Artemis II, no relay satellite was part of the mission's communications architecture. That was a deliberate design choice for a crude lunar flyby, not an oversight. Artemis II was designed for direct Earth-to-Orion contact throughout most of its trajectory. The 41-minute blackout was a planned, expected event, built into the mission timeline from the beginning, not an anomaly that caught anyone by surprise. Artemis II was not the first time a crewed spacecraft went silent behind the moon. Every crewed Apollo mission that entered lunar orbit experienced this. The moment the spacecraft crossed behind the moon's limb, Houston lost the signal. The crew was alone. The flight directors waited. There was nothing else to do. Apollo 17, in December of 1972, experienced blackouts during its lunar orbit passes. The duration varied with each orbit, a direct consequence of trajectory geometry, approach angle, and orbital altitude. What we know with certainty is that each of those orbital pass blackouts lasted longer than Artemis II's 41 minutes. That difference reflects a fundamentally different kind of pass. Apollo 17 entered full lunar orbit, circling the moon again and again, while Artemis II executed a single, faster flyby arc. The root cause was identical. The moon was in the way. What changed between 1972 and Artemis II was not the physics. What changed was the hardware flying through the shadow and the instruments measuring what happened inside it. Artemis I, the uncrewed test flight in November 2022, flew a distant retrograde orbit that kept Orion outside the radio shadow cone throughout the mission. Unlike Artemis II's lunar flyby, Artemis I's trajectory never placed the spacecraft behind the moon in a way that blocked direct line of sight to Earth, which means Artemis II was the first time Orion hardware, the actual capsule that carried a crew, experienced this blackout under operational conditions. That distinction matters more than it might seem. Pre-flight models had predicted how Orion's systems would behave during 41 minutes without ground contact. Thermal management, power cycling, autonomous navigation, all of it modeled against simulated conditions. But a model tells you what should happen. Operational data tells you what did. Artemis II gave engineers real data on how Orion performs in the lunar far side shadow. Thermal behavior across 41 minutes of isolation. Power consumption without ground commanding. Autonomous navigation holding trajectory without DSN correction. Crew workload during communication loss. All of it measured against actual conditions for the first time, because Artemis I's trajectory never put Orion in the shadow cone, and no simulation can fully substitute for the real geometry. That data feeds directly into every mission that follows, every crewed lunar orbit, every surface landing, every extended far-side operation. The 41-minute silence was not just an inconvenience. It was a measurement the entire Artemis program needed, and one that only the real shadow cone, cast by 3,474 kilometers of actual moon, could provide. If geometry is the problem, the solution has to be geometric. You cannot move the moon. You cannot bend radio waves around it. But you can put a satellite somewhere outside the shadow cone, somewhere with simultaneous line of sight to both the far-side spacecraft and to Earth, and use it as a relay. The signal goes up to the relay passes it across, the relay sends it down. The moon never enters the equation. This is not a theoretical idea. It has been done, and the mission that did it continues operating today. In 2018, China's space agency deployed a satellite called Queqiao, meaning Magpie Bridge, to support the Chang'e 4 mission, which would land a rover on the moon's far side. The far side had never been reached by a surface mission before, for exactly the reason we've been describing. No relay, no contact. Queqiao was placed at the Earth-Moon L2 Lagrange point, a gravitational equilibrium position approximately 65,000 kilometers beyond the moon, on the far side. From L2, Queqiao has simultaneous line of sight to the lunar far surface below and to Earth across the void. It sits outside the shadow cone entirely, not in orbit around the moon, at a gravitational sweet spot where the combined pull of Earth and Moon holds it in a stable halo orbit relative to both bodies, requiring only modest station-keeping corrections to maintain its position. From that position, Queqiao has relayed signals from the Chang'e 4 lander on the lunar surface to ground stations on Earth continuously since 2019. As of April 2026, Queqiao remains operational, making it the only relay satellite actively supporting a lunar far-side mission. It has demonstrated that the geometry problem is solvable, not by changing the physics, but by positioning infrastructure where the shadow cone cannot reach. Artemis II had no equivalent. The mission architecture was designed for a direct Earth-to-Orion link during the lunar flyby phase. A relay satellite was not part of Artemis II's communications infrastructure, and that reflects the mission's specific objectives. A crewed flyby, not a far-side landing. A direct link, not a relay chain. The blackout was planned, expected, and managed. The absence of a Queqiao-style relay was not a failure of imagination. It was a consequence of mission scope. Artemis II was never intended to operate on the far side. It was intended to pass through the shadow cone once, measure what happened, and come home. The Queqiao precedent makes one thing clear. The 41-minute blackout is not an unsolvable problem. It is an architectural choice. A relay satellite positioned outside the moon's shadow cone can maintain continuous contact with a spacecraft on the far side, The physics doesn't change. The geometry doesn't change. But the infrastructure around the geometry can. So here is what the 41 minutes of silence actually was. It was not a malfunction. It was not a gap in NASA's capabilities. It was not a problem that a bigger antenna or a better ground station could have solved. Goldstone was running. Madrid was running. Canberra was running. All three stations were active, pointing correctly, operating at full capacity. It was the moon's diameter, 3,474 kilometers of basalt and anorthosite, doing exactly what physics requires it to do: casting a shadow, blocking line of sight, making radio silence geometrically inevitable for any spacecraft on the far side without relay infrastructure positioned outside that cone. The fastest signals in the universe, traveling at the speed of light, crossing the Earth-Moon gap in 1.3 seconds, could not reach Orion during those 41 minutes. Not because they weren't fast enough, because there was no straight line to travel. Light speed is irrelevant when 3,000 kilometers of rock removes the path entirely. What Artemis II gave us, in exchange for that silence, was something engineers had never had before: real operational data on how Orion behaves when it is genuinely on its own. Thermal performance across 41 minutes without ground commanding. Power management without DSN correction. Autonomous navigation holding trajectory through the shadow. All of it measured against actual conditions, not models, because no simulation can replicate the specific thermal load, the specific power draw, the specific navigation drift of a real capsule in a real shadow cone cast by the real moon. That data is now in the foundation of every mission that follows. And the relay solution that Queqiao demonstrated? A satellite at Earth-Moon L2, 65,000 kilometers beyond the moon, maintaining line of sight to both the far side and Earth, is the architectural answer that makes continuous contact possible. Not by changing the physics, by working with it. By putting infrastructure in the one place the shadow cone cannot reach. The moon will always cast that shadow. The question is whether we put something in the right place to bridge it. That 41-minute silence is a reminder that space exploration is not just a contest between human ambition and distance. It is a negotiation with geometry. Orion crossed behind 3,474 kilometers of rock, went dark for 41 minutes, and came back with data no simulation could have produced. The silence was the experiment. Every solid world in the solar system casts the same kind of cone. Mars does it, Jupiter does it, the moon around Europa does it. Every future crewed mission beyond Earth orbit will have to negotiate with the same physics. And the relay architecture that Queqiao proved at Earth-Moon L2 is the template for how we answer it. The shadow cone is not the enemy. It is the exam. And Artemis II just showed us what passing looks like. I'm here to help you know the systems shaping our universe. Artemis II went silent behind the moon for 41 minutes. Which planetary blackout should we investigate next? Mars cuts contact for up to 20 minutes. Europa's shadow is even stranger. Drop your pick in the comments. See you at the next signal acquisition.